Hello, everyone. It's a great honor to present our work at IEEE VR. My name is Xiang Chen, and I'm from Beijing University of Posts and Telecommunications. Our paper is titled UbiGrip, Ubiquitous Grip-Based Tangible Object Utilization in Augmented Reality. To enhance the realism and immersion of user experiences in AR, existing research has explored ways to address the lack of haptic feedback when interacting with virtual objects. Tangible augmented reality offers a promising solution by leveraging everyday objects as physical proxies for virtual ones, allowing users to manipulate virtual content as naturally as real objects. For example, a mobile phone can serve as a proxy for a pointer, controller, or pen. However, we identified several limitations in prior work. The methodology for selecting appropriate proxy objects remains underdeveloped, mappings are largely restricted to one-to-one correspondences, and both real-time performance and generalization capability remain challenging. In this work, we aim to address these issues. First, selecting suitable proxy objects has always been a challenging problem. By reviewing prior research, we characterize proxy objects along two dimensions: physical properties and affordances. Physical properties are further divided into 6 key attributes: size, shape, texture, hardness, temperature, and weight. Shape is additionally categorized into 3 aspects: edges, surfaces, and graspable local geometry. As shown in figure, users can interact with virtual content by sliding along an edge, using a surface for button layout and clicking, or changing grips to map to different virtual objects. Affordances are further classified into specificities and commonalities. Specificities refer to widely recognized, usable behaviors of an object, such as the action of spraying water, while commonalities refer to general operable behaviors, including holding, rotating, and lifting. We then propose a framework that decomposes hand-object interactions into 3 components: object, gesture, and relative movement. This classification generalizes HOI into triples, which can be interpreted as the interactive object, the user's intention, and the interaction state. Second, previous work has largely been limited to one-to-one mappings. In our system, we achieve one-to-many mappings by varying the grip position or gesture used on the same proxy object, based on the HOI triple representation. A use case of UbiGrip is illustrated on the left. Here, the user employs a spray bottle as a tangible proxy. By simply changing their grip, they can seamlessly switch its virtual mapping between a gun and a mallet, allowing them to hit pig jars with the mallet or shoot targets with the toy gun. This interaction paradigm is deeply rooted in daily life, as grip-based manipulation is our primary means of interacting with physical objects. On the right, we extend this concept by presenting a taxonomy of hand-object interactions, using a mobile phone as an example. As demonstrated, different grip gestures, combined with relative movements, enable intuitive switching between various hand-object interactions. Third, our system ensures both real-time performance and generalizability. The figure illustrates the overall framework of UbiGrip. To begin, users capture a single image of the target object. We leverage a 2D diffusion prior to generate multi-view images, then apply 3D Gaussian splatting to reconstruct the object's point cloud. Finally, mesh extraction and texture refinement are performed to obtain the final object model. Based on the reconstructed mesh, we build a sparse viewpoint model to efficiently represent the object's contour for tracking. We extend a classical region-based method, SRT3D, to enable high-speed tracking under challenging hand-object interaction scenarios. Meanwhile, the Hamer model is adopted for 3D hand pose estimation and hand mesh reconstruction. To mitigate the impact of hand occlusion on object tracking, we propose a filtering strategy. Before performing pose optimization, we compute the pixel center of each correspondence line and filter out those whose centers fall within the hand mask. However, when occlusion is severe, an excessive number of correspondence lines may be filtered out, leading to degraded pose accuracy. In grip-based interaction scenarios, the relative hand-to-object pose remains relatively static. Therefore, it is reasonable to propagate hand motion to the held object. We introduce a user-defined tangible control workflow that uses grip-based trigger actions to activate interactions. As shown in the figure A, the user's right hand grasps the proxy object, and the left hand clicks a button to record the physical grip. B, the user's right hand grasps the virtual watering can, and the left hand clicks to record the virtual grip. Note that the transparent hand indicates the currently active hand, while the solid white hand represents a defined gesture. The same workflow applies to C and D. We implement a grip matching algorithm that evaluates the similarity between the current hand gesture and pre-registered grips based on distance thresholds and transformation analysis. The following formula computes the similarity in both position and rotation between the current gesture and each defined grip. The grip with the highest similarity score is selected for the final mapping. In our evaluation, we reconstruct objects from the DEXYCB dataset. We present multi-view reconstruction results for 3 representative objects, which largely preserve shape and texture fidelity. As shown in the table, evaluation metrics using our reconstructed models, 4th column, are slightly lower than those using ground truth models, 3rd column, yet still outperform state-of-the-art methods. Specifically, our method achieves an average ADD 0.1D of 57.9%, surpassing the SOTA method by 27.7%, highlighting its effectiveness. On the HO3D dataset, our method attains an average ADD 0.1D score of 87.3%, outperforming prior work by 13.6%. We also conduct an efficiency comparison on the HO3D dataset, measuring per-frame latency on a single RTX 3090 GPU. Our approach achieves lower time costs and is training-free for new objects, enabling seamless generalization to everyday objects. Additionally, an ablation study on the HO3D dataset shows that our optimization strategies yield a 2.1% improvement in ADD 0.1D over the baseline. Finally, we conducted a user study. We selected 10 everyday objects as physical proxies. As shown in the figure, each participant completed 3 interaction scenarios involving tasks with varying numbers of switching interactions. Each scenario included 2 mapping modes, 1-to-1, O1, using 2 dedicated proxies, and 1-to-2, O2, using a single coproxy for both virtual objects. The results indicate that using a coproxy did not significantly reduce the perceived quality of haptic feedback. Moreover, both O1 and O2 grip definitions introduced no additional time overhead and were found to be user-friendly. The one-to-many mapping approach shows potential for improving interaction efficiency. For more detailed results, please refer to our paper. That concludes our presentation. We hope this work offers valuable insights for future TAR applications and contributes to the advancement of the research community. Thank you for watching.